My name is Viraj, and I've been a volunteer. There are a bunch of volunteers out here also. SIPA is Silicon Valley Indian Professional Association, and we've been hosting quite a bit of these talks. We've done that, I think, for the last 12 years, I guess, more than that.
87.
87. So quite a bit. We have, kind of picked up the pace the last couple of years. We have some of the other event every month or every alternate month. This year we've been able to keep it on a monthly basis, but what we have today is, we are trying to start a new kind of set of sessions, and mostly with the theme of machine learning. And we are going to start with the first one with SK. I'm going to give 2 minutes to Mark because we have got this particular venue by TechCode. So, Mark, why don't you talk 2 minutes about TechCode, and then we'll get back to introductions of SK.
Thank you. I don't need the mic. So I don't think I need 2 minutes either. Thank you all for coming. My name is Mark. I'm an investment associate here just for the summer. I'll be a senior next year. For those of you who don't know much about TechCode, we're a global incubator, accelerator, and venture capital fund headquartered out of Beijing. We have roughly 30 international offices in Berlin, Tel Aviv. We're opening more, it seems like every day. And just recently we started our AI Plus Accelerator. So it's a rolling cohort system. And we're right now just focused on recruiting high quality startups that we can feed into the pipeline so they can land in China, where we intend to provide them with all three types of capital: financial, human, and intellectual. If you guys have any questions, I'll be at the front desk. I'd love to give any of you guys a tour or just speak more about TechCode. But thanks for coming, and I'm sure you'll enjoy the event. Thank you.
Thanks, Mark. So I think I'll spend a minute to kind of tell you how I met SK, and I met because I was interested with machine learning meetups, and SK runs one of the meetups in Cupertino, and with SIPA we were looking at machine learning and starting these particular workshops or talks. And basically that's how I met. It's been how many, 2 or 3 months that we met, but a little bit on SK. He's a serial entrepreneur. He has already kind of completed 2 companies, and on the third, that's his track record. He's an avid blogger, mostly with machine learning, and does a lot of research around that kind of area. So I won't take much time, but I'll give the mic now to SK.
Thank you. I don't need the mic too. I can actually talk without it. So
all right.
Yeah. Thank you everyone for coming. Hope I'm loud enough. I'm going to talk about language translation. In the last year and a half or 2 is when the section of machine learning called natural language processing has really taken off. If I have to give a little more context, the machines that can process more text have been invented only just a year and a half and 2 years ago. The frameworks that can actually process text and make sense out of the text also have stabilized in the last 6 months. Actually, one of the most famous ones, TensorFlow, the first finalized version of TensorFlow was released in January of this year, 1.0, now it's 1.2. The whole of last year and a half, it was various draft versions of TensorFlow. So within machine learning, if you look into the section called natural language processing, has taken off only the last year and a half. Stanford, Harvard, and some of the big companies like Microsoft and Google, they've been actually doing a lot of research on NLP, but if you don't find too much of talent in the industry yet. Machine learning, I would say, if I had to put in a few words, is that area which actually processes numbers, just pure numbers, whether it's a stock market prediction or weather prediction or preventive maintenance of aircraft or medical patient history. Any of these activities is pure processing of numbers. But processing of text has not been that popular till a year and a half or 2 years ago, and after it got taken off, there's so much of research focus on how to take wisdom out of text as it is and also combine numbers with text. Let me give you a few examples of text processing. If you have a large number of documents in a company, and if you want to find out, let's say it's a patient record, or if it's a product information about your company, and if you're a sales guy and you want to suddenly find out, hang on, 6 months ago we made a sale to a customer in Boston, what was the deal we made and what was the questions we found? And unless you have a human being working in the company with long institutional knowledge who can recollect the answer, it's humanly not possible to find out the information. So in NLP, there is a section called question answering. So you actually can feed in lots and lots of text and you can ask questions. So when I say question answering, let me give an example. The question answering is not similar to pattern matching where the computer will go look for a specific word and then outputs the answer. Here is a story. Sally went to the kitchen, John went there too. It was morning, weather was really good, and Sally said a hi too. If you tell this story and say, okay, Sally said a hi to who? As a human being, we can figure out, oh, Sally said a hi to John. But if you ask the question to the computer, so you got to first, computer has to figure out Sally is a human being, and she has to be obviously saying hi to another human being, mostly, unless Sally is like me. So, and also, nowhere in the story it's mentioned John is in the kitchen too. I said Sally went to the kitchen, John went there. So comprehension of text and consequently answering the questions is one of the areas of focus within NLP. Similarly, you have comprehension where you are trying to summarize an abstract large amount of text, whether it's a news processing organization or if it's or any organization which is trying to summarize text. Computers can very intelligently process the text and intelligently, really intelligently summarize in a shorter and a fewer words. Language translation is another focus area within NLP where you feed in the text, and it can be a text to text, of course voice to voice too, but I'm going to talk about the text to text translation of language. And the complexity of language translation, I just want to talk about that. English, the way you form a sentence, the structure, the subject, object, and the verb and all of those things, is not the same structure you find, let's say, when you go to Chinese or Japanese or even German. Some of the European languages are a little bit similar to English, and hence there's more research results available in language translation between English and some of the European languages. But it becomes a lot more difficult when it goes to, let's say, Chinese, English to Chinese, or English to Japanese, where sometimes the first two words in English sentence will have an impact on the last two words of the Chinese translated sentence. So in machine learning, I think, especially in NLP, the networks, especially the neural networks, the deep neural networks, have to understand and memorize some of the information so that it can actually process it. So we're going to talk about that. Historically, if I had to give a historical perspective, I think 5 years ago, 10 years ago, there used to be rule-based and example-based machine translation, which is where people, I think, used to sit down and then try to do some translation. And later on came statistical machine translation, where you have large amount of corpora available. When I say corpora, huge amount of text available, and let's say in English and let's say German, and then you have translations of the English sentences in German, and you actually have the one-to-one map to the sentence. And so you actually have a bilingual corpora available, and then you can do statistical analysis. When I say statistical analysis, let's say you find a two-word phrase in English sentence, you will go look into the dictionary of this corpora to find what is the equivalent two-word or one-word or three-word translation in the target language, and do statistical probability on that, and then bring it down and then put the translation together. But in the last year and a half, two, the deep networks, neural network implementation of language translations have come in. There's a lot of progress that has been made. There's one indicator. I want to talk about the indicator, and then we'll talk about how the translation is done. How do you know that machine translation is actually accurate? It's coming closer to the human translation. there is a metric called BLEU score, BLEU, Bilingual Evaluation Understudy, which is a metric that shows how closer is this translated sentence to a human translated sentence. The word human translated sentence is also called as ground truth. In other words, if you have an English sentence, if you have a German translation done by a human being, that sentence is called the ground truth, and then you ask the neural networks to actually translate it and tell what the translation is. Once you have the machine translated sentence and the human translated sentence, you can see how far away they are, how far apart these two sentences are. But the endeavor is to actually bring it as close as possible. So BLEU scores varies between 0 and 1. A score closer to 1 means it's very close to the human translation, and 0 is the opposite. When machine translation started a year and a half ago, 2 years ago, the BLEU scores was only 20%, so it reflected in percentage, 20, 18%, 20%. Right now there are 42% is the BLEU scores of machine translated thing. So if you have a sentence in English and you have a translation done by the machine in German, the accuracy, if I can use the word accuracy in this context, is 40%, which actually is a tremendous progress compared to 20% a year ago, year and a half ago. And also, it's also a tremendous progress because of neural networks, the speed with which they're doing it, and the ease with which they're doing the translation. Of course, there's a long way to go. Just a few minutes ago, I was telling someone that we're all, I think, midst of this real transformation happening in the machine learning world, or even the natural language processing world, where maybe 2 years from now, 3 years from now, you may see a perfect or a score of 1 or 100% human translation type happening by the machines, and I'm quite confident of that. But today, let me talk about various techniques one can use to do the translation. I will try to explain these concepts on two different fronts. One is, I will try to explain the concept to make it, I'll try to make it as simple as possible, and so that I think we understand the concept, and then I'll try to after that explain mathematically or how the deep learning activities happen to process this information, and I'll explain the concepts in that context too. I will try to avoid as much of mathematics as possible, but ML or NLP, there's no place, there's no way you can avoid mathematics. So I'm actually going to have a lot of mathematical equations in my slides, but I'll try to explain with and without mathematics to the extent possible. And I'll also talk about very quickly implementation of it, because that's one of the major missing points I've seen in when I attended many meetups. People, I think, talk about more of what, but less of how people are doing. But I cannot do all of those things in 1 hour. After that, I think it's going to be boring for you. And I remember talking about anything longer than an hour, long time ago when I was still young. I was teaching in a university as a hobby and as an adjunct faculty. I was going for my first class and I was very nervous, and I asked a very seasoned professor, give me a few tips. How do I make sure students like me? Otherwise, I don't want them to get bored. He said, watch out for the body language. The moment they stop listening, stop talking. I said, okay, fine, but how do I know they stop listening? He said, 2 or 3 body language. One is, if they're all sitting, leaning back and crossing their hands, and they just don't have any facial expressions changing in the face, that means they're done. Okay, so I'll be constantly watching your faces. The moment I feel that there's no response coming from you, I'm going to stop. Yeah, but I'll try to keep it as simple as possible so that we can all understand. So these are all the various techniques used, but the most fundamental, the sequence to sequence or encoder decoder, are the 2 fundamental building blocks for machine translation. Of course, there are also building blocks for other NLP tasks like question answering stuff too, but we'll focus only from the perspective of machine translation. And then all other techniques are enhancements to those to make sure the BLEU score goes up higher, or the translation is more human understandable. Also, let me clarify the word BLEU score. The way the BLEU score is computed is it's the number of words in the machine translated sentence that match with the words in the human translated sentence. But the problem is the sequence of words is not really given importance to. So that means if the machine translation screws up on the sequence of the word, the sat, cat, mat on the mat, instead of saying the cat sat on the mat, instead of, if you say the mat, cat on the sat, you still get a high blue score, but it doesn't make sense. So these techniques will enhance not just the blue score, but also they're bringing it more closer to the human understanding. Before we get to sequence, the most popularly used, I think used to be used, neural building block is RNN, recurrent neural network, which actually takes an input and then gives an output. And it constantly remembers what it has learned until now. So time step T, it knows what it has learned and it's constantly outputting things. And it can go any number of steps depending upon the inputs you're giving. So it's actually called unfolding of. So if you have a sentence with T words, T number of words, 0 to T, it keeps on taking one word at a time, at a time step 1, 2, 3, and then processes that word and then outputs an output. Now, when I say you input a word, you're actually converting the word into some vectors. And there are a lot of techniques available how to convert a word into a vector. A year and a half ago, you got to write yourself word embeddings, it's called. But now you have programs where you can just word to vec or glove vectors, which actually immediately translate a word into a number. So let's say you already have figured out how to translate a word into a number. So you keep on inputting one word at a time into neural network, RNN, and then it keeps on outputting. So if you have a sentence, I went to the movies and enjoyed it. And if you want to translate that into, let's say, German or Chinese or whatever, you input each word at a time and it's processing. And at the end of the sentence, the RNN knows that you're done with the sentence. Now it's my time to start translating that. And I'll talk about how it knows. Also, RNN, when I say it remembers, why does it have to remember things? It doesn't remember each and everything, but it remembers some important details. For example, if you look at the first sentence, he doesn't have much confidence in himself. By the time it comes to translating the word himself, the neural network has to remember the gender of the subject. Otherwise, you'll end up doing himself or herself. So that's the amount of information the neural network remembers. Now, how does it remember? That's a sort of magic. It remembers. Because you're training the model with large amount of data and it slowly gets smarter and smarter. Okay, talking about RNN, people found there is one problem in RNN. The longer the sentence, the difficulty RNN had in remembering details. It remembers maybe around 6 to 7 words in the past. It doesn't remember, let's say, a 10 word or a 15 word, 20 word sentence. So there's a new invention called LSTM, long short-term memory. This is a variation of RNN, but there's a lot more mathematics happening in this. So every time you input a word into the LSTM, it does lots of mathematics. You can see so many equations here, and if someone is curious, I can even explain the equations. But what's happening is, it processes the number and outputs something called cell state and a hidden state. But it's actually the hidden state which is most important. Hidden state is the intelligence of the cell till now based on the information you have fed in. In the previous sentence, let's say he doesn't have much. Whatever intelligence, whatever information that part of the sentence gives, it actually understands that. That's what it's doing while it's processing, and the hidden state is actually a vector. And if you do softmax on the vector, it actually tells you what may be the next word. So I'll explain more of this going forward, but let's say compared to RNN as a building block, LSTM has even a more appropriate and relevant building block of late. almost all the research for the last 6 to 8 months happening on language translation or summarization has been happening on LSTMs. A few research is focusing on a variation, further variation of LSTM called GRUs, gated recurrent units. They're almost LSTMs, but they don't have, LSTMs has 3 gates, but GRUs have only 2 gates. And when I say gate, the F and I is called forget gate and input gate. Forget gate is a mathematical process on your input which will tell the cell how much to forget from the previous text. And input is when when the new input comes, it adds the new input to the current understanding. And current wisdom or understanding, whatever it is called, hidden state. And it's a vector which is constantly learning. So now this is where the real translation is happening. So you take a LSTM and you start inputting word after word. It reads each word, and at the end of the sentence, typically all scientists in their research, when they do research and translation, the way they tell the model that it's now the end of the sentence is you have a special end of the sentence character. It could be just something called EOS as a character, or period as a end of sentence character. The moment it encounters the end of sentence character, it knows that now it's my time to translate. So this is the most fundamental block called sequence to sequence. So you actually are inputting a sequence of words and it outputs a sequence of words. That's where the word sequence to sequence comes. So let's say if your input sentence is ABC, so at every time step you input a word A and B and C, and then after that it will be end of sentence. The moment end of sentence is encountered, it starts outputting the translation. The translation word is WXYZ, and then end of sentence too. And when it outputs end of sentence, the model knows that I am also done, and then it stops doing things until you start maybe inputting the next sentence. And when you translate A, when you input A and then it goes to B, the hidden state is constantly getting modified. And after B, the hidden state has an awareness of both A and B. And after inputting C, the hidden state has an awareness of A, B, and C. And then similarly, when you're done with the EOS, it actually has the awareness of that. And when you start outputting W, because it knows the entire sentence, theoretically what you can do is, you can tell the model, okay, I have given you all the input sentence, you go ahead and give me the output sentence. So it outputs W first, and then it has to output X. After initial research, scientists found that many times you tell the model what was the word you just now output. So when you reintroduce the word W back into the model, the accuracy of the word X prediction goes up. And hence, every time step, you're inputting the previous output. And so from A to B to C, you have a hidden state constantly getting modified. After EOS, it's the same thing. And this change in the hidden state will continue until it encounters the end of statement in the output, but it's outputting the translated sentence too. So I want you to understand this fundamental process. The same LSTM or GRU takes a sequence of words and it internalizes those words by having the hidden state update, and once you're done with the sentence, it actually starts translating the sentence using that hidden state. So the hidden state vector is the most important a factor or a detail or information that RNN or LSTM it needs. Now, all future research is focused on how do I make the hidden state calculations more intelligent, and how do I make the neural networks more stronger or more intelligent. And I'll talk about various techniques after that. So the mathematical representation is P is probability of Y1 to YT, that is probability of the output word Y, YI, let's say, the vertical line is given. So probability of y1 to yt given x1 to xt is the product of the probability of each probability of yt given the entire. So probability of the current output is dependent on the hidden vector v and all the previously outputted words. And this mathematical implementation I'll show you also in how to do in an actual program, in Keras programming. This is another representation of of the same process, what I mentioned earlier, sequence to sequence, but scientists came out with a new notation called encoder and decoder. So instead of having one single LSTM, they said, okay, we're going to have two LSTMs. One LSTM reads the input sentences, creates a hidden vector, and passes on that hidden vector to the next LSTM. So next LSTM, it gets two inputs. One is the hidden vector from the previous, and maybe the first word or the end of sentence token, whatever. And the decoder with that hidden vector starts outputting words. So it's the same concept instead of having a single cell, and people have started calling encoder and decoder. As the words say, encoder takes the information in the source language. Typically in translation, we call source language and target language. Source language is what you're translating from, target language is to. So encoder actually takes the sentence in the source language and translates it into the target language. And this is the same thing too. So you see H1, H2, H3, these are all the hidden vectors which the system is creating for itself, and then it passes on the same, and then so the red vertical blocks are the encoder cell, let's say LSTM, which is unfolding 3 times because there are 3 words coming in, and the decoder LSTM is a different LSTM which unfolds twice because it only has 2 words in the translated sentence. So this is the mathematics of it. In the encoder, you compute the hidden vector or hidden state, and hidden state is a function of the current input xt at time steps t and the previous hidden state. So every time, at every time step, the LSTM creates a new hidden state based on the previous hidden state and the current input. And the output vector is a function of all the hidden states. So if you have 3 words, inputting words in source language, and if you have 3 hidden states, and the output is a function of all those 3 hidden states. Decoder is a probability of yt at time step, that is the output at time t, is factor of the context vector, which is the vector you compute based on all the hidden states. So the yt output is a function of all the previously outputted words and context vector c. What is hidden state? So in the LSTM, at time step t, you have the word x being input in, and it has the previous hidden state coming in, and also it's called cell memory state coming in. There's a lot of processing that's happening. I don't want to explain it now because I think I don't have time to cover all, but you have the forget gate, input gate, you have a candidate context, then you have the memory vector, output vector, and then the hidden state. You do all of these computations to identify what the hidden state is. So when you input the new word and the previous hidden state, it gives the new hidden state, so at every time step. And the hidden state is nothing else but a matrix. It's a massive vector, 2 by 2, or it could be even a higher dimensional matrix too, which actually is an encapsulation of all the information, semantic, understanding, or other relevant information of the input sentence till timestamp t. And that's what the time step. So you actually compute the hidden state constantly. Every time step, hidden state changes. And the hidden state at any point of time, will capture information about all the previous inputs. So that's how the encoder and decoder is defined. And another way of looking at an encoder decoder is this is just I'm representing slightly differently. Otherwise, it's the same concept. So you have the encoder where you input a series of words from x1 to xt, and at the end of the sentence, you have a context vector created, and that context vector is given to the decoder. But in this particular experiment, which was mentioned here at the bottom, they not only give the context vector at the start of the decoding process, but they also give the same context vector at each decoding process. So let me explain that. So when the decoder starts, it gets the input of the hidden vector from the encoder, right? And then it starts outputting the first word, that is y1, y2, y3. Every time it outputs a word, it's changing its own hidden state. And it goes to the next step, looks at the new hidden state and identifies the next word, y2, y3. But in this encoder decoder with a peak, at every time step, that is even at the time step y2, it not only looks at the previous hidden state of the decoder, it also gets the context vector one more time. So it actually has additional information coming in at every time step. So it's actually peaking at the original context vector. So when you're done with y1 and when you go to y2, the context vector, so the decoder will have its own context vector, hidden state. Sorry, let me repeat. The decoder will have a hidden state, but instead of depending only on the hidden state of decoder, it actually goes back and looks at what was the original context vector that was shared with the first, and then based on those two vectors, it outputs the y2. And similarly at yt, it looks at the previous hidden state and also the context vector initially that came in. So this only enhances, because it remembers, the context vector C has a lot more information compared to the current hidden state of decoder. And that's why in this approach, you also give the original context vector as an input to decoder at every time step. When human beings do a translation, let's say you have a long sentence, and let's say it's a 10-word sentence, and if you have a 5-word or a 7-word translated sentence in a target language, by the time you reach the 3rd word or a 4th word, you may want to go back and check, hang on, what was the 4th word in the input sentence? Even though I have the context vector which encapsulates the entire input sentence, sometimes you may want to go back and check one more time. And that's called attention. So the decoder has the context vector, but also says, wait, I want to go back and check what was the 4th word, because you have not captured the actual 4th word for me in the hidden state. That's called attention. So when you are translating into a sentence, once in a while the neural network wants to go back and look at your input sentence at certain timestamps, and it wants to go back and look at certain portions of the sentence, not the entire sentence, because it doesn't want the entire sentence. Only 1 or 2 words it needs for this current word translation. And that's attention. And there's a very, very simple mathematical equation where you see this is the encoder, and there are, of course, you can see arrows on both sides. It's called bi-directional LSTM. Let's ignore that part right now. Let's say you have the encoder LSTM, which is outputting hidden states at every time step, but instead of taking the entire hidden state, we take a weighted average of all the hidden states, which is computed by alpha, the AT, at time step AT. It's a weighted average of all the hidden states, which will go as an input into your decoder. That's an attention mechanism, in decoding process. So let me recap. In the most fundamental block, you give an input of a series of words, and using the last hidden state, it starts outputting the sentence. People felt this is not sufficient. They said, okay, let's have two separate LSTMs. One is encoder decoder. You take the last hidden state and give it to the decoder. After that, they said, no, it's not sufficient still. So once we do the decoder, and if the decoder hidden state goes into decoder and continues, it wants to peak at the original hidden state. And after that, people said, no, not just the original hidden state. I won't even know what was the hidden state at fourth word or the third word, and that's called attention. So it actually goes back. So these are all the steps people are invented to enhance the blue score of the translation. Now, these all look very complicated, and this is another model which actually talks about when you do a translation of words, sometimes they even want to focus on individual characters. I think in certain character-based languages, like even Chinese and other languages, where sometimes you may want to go back and translate just one character, not combination of characters. So this is another attention mechanism which actually focus on the characters, but the underlying principle remains the same when we say attention. This is another attention example, so you can, what I'm trying to say is, you can implement attention in different ways. You can just make it more and more complicated. Till now, I was only talking about, when I say encoder or decoder, I only said there's one LSTM and one LSTM. But you actually can have as stacked LSTMs too. You can actually have two LSTMs or four LSTMs as encoder. And then all of that together will process the information and then gives one complicated hidden state to the decoder. Now, decoder itself could be stacked LSTMs. It could be 4-layer, 2-layer, 8-layer LSTMs. And there's a lot of research done too. Is it good idea to have more and more LSTM layers? And the results in this particular research, if you look at the paper, first of all, LSTMs are better than RNNs in doing translation. And sometimes the shallow network, that is, you don't need to have 20 layers of LSTM. Sometimes even 2 layers, 4 layers, 6 layers also are fine. After 8 layers, I think the efficiency drops. So it's more of computationally expensive, but it doesn't give a higher blue scores. And also, if you have deeper and deeper, that is denser and denser, or more and more layers of LSTMs, even optimizing the numbers is not an easy thing. Okay, then so let's take a quick stop and then say, okay, how do I implement sequence to sequence? It's just a one-line program. If you use Keras, you call the model. Model is equal to simple sequence to sequence, and you give an input, hidden state, output length, and output dimension, and that's it. You have defined a simple sequence to sequence model. And if you actually want to have sequence to sequence with a peak, just one parameter changes. Peak is going to tell the truth. And if you really want to implement attention, which is so complicated, it looks like if you look at this math, but to implement the attention, all that you have to just call the attention model. So model is equal to attention. Model is equal to attention sequence to sequence, and that's it. It actually implements attention. So even just a year and a half ago, when you do an implementation of neural networks, when you're training a neural network, there's something called back propagation. You actually input a data, and the neural network outputs an answer, and if the answer is not correct, you want to go back and modify the various parameters, the weights in the neural network. That's called back propagation. And that was computationally very expensive. And just even a year and a half ago, people were writing back propagation mathematical equations with hand, also used to program with hand. But now in the last 6 months to 8 months, maybe a year, now you can just call a single API and that's it, you're done with the back propagation. And that actually has improved the productivity of software engineers and neural networks tremendously, because back propagation computations is tedious, buggy, and complicated. Now it's on a single line. So whatever I explained till now in the fundamental blocks, even though there's a lot of mathematics, a lot of It may sound the concepts are complicated, but the programming is extremely easy to write, implement that. So now let's, even though there's just mathematics here, I'll try to explain without mathematics. When you have a language translation, how do you train a model? You first take a bilingual corpora, that is, you actually have, let's say English to German, you actually have lots of sentences in English, and then do a translation by a human being in German. So you have a sentence 1, a comparable sentence to sentence 1, sentence 2, sentence 2, and then you start inputting those sentences into the neural network and you're training the model. And the more corpora you have, the more database you have, the smarter your model becomes. Now, the encoder decoder works exactly with that. You have a bilingual corpora and then you translate it. So you have one specific language called English and one that is source language, one specific target language, let's say German, and then you translate. But then some people said, hang on, can we use something called a language model in addition to a translation model? So TM and LM. What is a language model? Let's take a monolingual corpora. Let's say you have Wikipedia, okay? Take all the entire Wikipedia text. You have so many different topics and so many sentences. There are millions of sentences, right? Let's take one example sentence. Let's say the cat sat on the mat. When you feed in this monolingual corpora into a neural network and you create something called a language model, what the model is, it can predict what the next word would be. It's like almost like a human being. You train a human being on a language and you know what is the right word that comes after this sentence. Let's say the cat sat on the, and if you ask the language model, what is the next word? With a reasonable amount of confidence, the model says the next word is mat. And the next word being, tiger is very low probability. So it actually gives the probability of the next word that should go, which will fit into this sentence. That's called language model. Language model is another neural network which is trained on a single language. So people said, okay, you have a translation model which actually translates a sentence x1 to xt to y1 to yt, and the y1 to yt is dependent on the hidden state of the encoder. But can we enhance the accuracy of this translation by also adding up a language model? So the machine translation network gives a sentence, you give that sentence to the language model, and language model will tell you how correct this sentence is. So that was the proposal. There's something called a shallow fusion and a deep fusion. I won't get into the details, but in both the approaches, the scientists actually proposed, in addition to using just the hidden state of the encoder, we can also use the hidden state of the language model too. So in other words, I think you're giving more and more tools to your neural network model to make a better translation.
One question: would this language model be a reflection of the grammatical rules?
Yeah, it'll figure out the grammatical rules too. Yes, yeah.
And you would find that model separately from the.
Yes, yeah. There are pre-trained models available. If you want to take, let's say, an English language model or a German language model, there are language models available already. You can just but if you want to train it yourself too, and that's easy too. The reason why some people want to train their own language model is, if your corpora and your dictionaries are so specific. If you take Wikipedia, it has all sorts of information. It has medical information, technology information, and political information. But let's say you're a hospital and you're trying to develop a language model for hospital context. So the terminology is so specific for the medical world, you may want to take only the corpora that's available for medical world and train a language model based on that particular. Otherwise, you can take a generic one. So if you go to Google Translator right now, they have trained a Google Translator on the entire corpora available in the world. But let's say if you're a medical, it's a hospital, and if you're a doctor, if you want to do your translation, sometimes the translation may be erroneous because the language model trained on the entire massive world data is not intelligent enough to figure out what's the right word in the medical context. Because the medical related information is only a small part of the bigger corpora the model is trained in.
It's a generic model.
It's a generic model, yes. Yeah. Yeah. So sometimes you may want to train and sometimes when you train the model yourself, it's even faster because your corpora is smaller and the translation effort is also lesser. Let's say if you're a product company, if you're a technology company, if an airlines company, the type of corpora of the dictionary is so different from the word generic corpora. So in the translation, many times what happens, the encoder is trained on certain dictionary. You have, let's say, typical dictionary size is 30,000 to 80,000 words. So there's so many words in the encoder dictionary, and you have around 30 to 50,000 words in the decoder dictionary. In other words, if you give any sentence in the source language, if there is no relevant word in the target language, the dictionary of the target language, the model cannot figure out, oh, what should I say here? Because it doesn't know the right word. So then it introduced something called unknown, UNC. So software engineers, I think we know, we just put UNC wherever I think we don't know. So the decoder in that particular word, because it doesn't know what the word is, and it knows it's not in any of my 30,000 words, it is some other thing. So you actually have a special word called UNC. If you don't know the word, put UNC there. But if you cannot have too many UNCs in your translated sentence. Let's say I went to the movie today in the morning. I enjoyed the movie. That's an English sentence. But let's say if you are writing in German, I don't know. Alberto, you speak Spanish. So in the Spanish, if you have out of the 5 words or 6 words, there are 3 UNCs. You can't figure out what the meaning is, and it's not really a rich translation. So there's a lot of focus on how do I reduce the number of UNCs. One simple solution can be, why can't I have the dictionary bigger in size? Let's say, why can't I have 100,000 words, maybe 1,000,000 words, so that there's no way you don't have the word. The word is right there. But the problem with this, the computational cost will be tremendously high. Why? Every time the decoder predicts a word, how is it actually predicting? It's giving the probability, it gives a probability score for every word. The 80,000 words, it gives a probability at every time step. Obviously, the probability of the wrong words will be 0.00007, 0.00008 or whatever, and the probability of the right word may be, I think, 0.85, 0.92. That's where the probability is, and hence you pick that. But if you have 1,000,000 words, it's actually computing the probability of 1,000,000 words every time step. And it's going to be very expensive, it's going to be slow. So if you are to balance, so that people are trying to figure out, how do I minimize the number of UNCs? One way of doing it is, in some language source to target language, they figured out, by breaking down the word in the source language into smaller pieces, sometimes you can figure out. Let's say, I'll give a random example. If there is a word called running in the source sentence, and let's say the target's language, there is no equivalent translation for the word running. But there may be a translation for the word run. So when the model does not know what is the translation, it goes back and then starts breaking the word into smaller pieces. And then starts putting the word together to see, oh, did I form a word now? Maybe it'll break running into RU first. It says, no, RU doesn't make sense. RUN. Oh, RUN makes sense. Maybe there's a translation for that. So, and then ING, there is no translation for ING. So, based on the rules you have given, based on the wisdom you have taught the model, it finds the translation for run and puts an UNC-like character right next to the ING for ING in the target sentence. Now, at least you know it is some run-related word, even though you don't have the complete word there. So that's one idea people are looking at, where if you have missing words, you try to break the words into smaller pieces and then do it. Also, let's say you have a source language and target language corpora available, and you're training the model. And you also have a language model for source language separately and target language separately too, right? And now, instead of creating a model, a neural network model training on from the source to the target, why don't you create or train another model, train it from the target to the source? So in other words, let me explain. So you have English and German. You create a model which knows how to translate an English into a German sentence, but you also train another model which actually translates German into an English sentence. So you actually have two models. And for the reverse model, from the target to the source, pick a language model or a monolanguage corpora, club these two to create more data in your source language. So you're actually enriching your data set using the same data. You want to explain that one more time, or you got that? So you have the source and target. Instead of training only from source to target, train another model from target to source and pick a monolingual language model on the target, and using the language model and the translation model, create newer data on the source, and then you combine the source and the source, and then you have more data set to train. But let's say there is in the process of translation, the cat is the two words, and the next word, it says sat, and the cat went, and the cat ran, let's say. These are the three words that got relatively high probability. The cat sat, the word sat got the highest, but the immediately next probability was the cat ran. If you put the word ran and the word that comes after that, versus if you put the word the cat sat and then whatever word comes after. So you're actually talking about different sentences, entirely different types of sentence forming based on the word you pick right now. So at time step T, instead of picking only one word which has the highest probability, you actually pick a few more words, because you never know how the next word is going to be, and that may make more sense just because you made one wrong step. It's like chess. At every step, focus on not on the winner, focus on the loser. At every step, the losing candidate is actually making a perfectly sensible move, isn't it? When you play chess? But eventually, he loses, he or she loses. If you pick the one word which makes the highest probability, maybe that may eventually lead to a wrong sentence. So people have figured out that instead of picking only one word, pick a few words. And it's called, how many? It's called top K words, top 5 words, 3 words, 10 words. And that's called beam search. So instead of having only one word, pick 4 words, and for each of those words, identify what would be the next word. And you'll have how many sentences? You'll have K times the N being the vocabulary, because you have 4 words you pick, but you have 50,000 next words coming in. So to make it simple, identifying and remembering more and more words will help you diversify your sentence, and maybe the accuracy improves in the process. And how would you penalize the wrong word or wrong sentence? There's an algorithm given here. If you have a sibling words and you have the parent word, that is word at time step T and the word at T minus 1, all the siblings of the parent, each parent, except the top one, will get a lower score, and then you actually eliminate those siblings and you again get top K words. But anyway, this actually will enhance the diversity in the target sentence. This was another trick people have used about how to augment the amount of data you have. You have training models where you go from source to target, and then you also create source, target to source, and then you actually have richer models which are working together to help you translation. That's another trick people have used. I'll talk about the Google actually around 6 months ago, 8 months ago released their translation model for the public, and they even published a paper too. This is almost like the best paper I think in the last 8 months. Maybe I think there may be one or two couple of other papers that have come. I've not studied it yet, but this is kind of the best paper. Google used so many techniques, some new, some old, into this technique, and this model is really of very high accuracy. For example, they have used 8-layer encoder and 8-layer decoder. So actually, the richness of capturing the source sentence and translating to the target sentence is higher. Also, in the encoder at layer 1, at the bottommost layer, they've used a bi-directional LSTM. What is the meaning of a bi-directional LSTM? Imagine there is a 5-word sentence, the cat's out of the mat. For the forward moving LSTM, you input the first word at the first time step, and then the second word at the second time step, and you go in that direction. But in the reverse LSTM, at time step 1, you introduce the last word. At time step 2, you introduce the last but one, that is -1 word. So you're actually introducing the sentence in the reverse way. So, let me show you a different picture for bidirectional LSTM. So here, in the encoder, you have a bidirectional LSTM where you input for the forward-looking LSTM the correct sequence of the sentence, but for the reverse, you will introduce in the reverse way. So you introduce the last word, second last, third last, and the first word. And at every time step, each LSTM will have their own hidden state, and you concatenate these two hidden states. So at this time step, let's say, and whatever concatenated hidden state that comes out, it is this hidden state will know what is this word, and when you concatenate, it also knows this word and this word and this word and this word. So the concatenated hidden state will be aware of 4 different words, not next to each other, but somewhere very much apart. That enhances the richness of the hidden state. So bidirectional LSTMs will actually capture that information. But they did not do it for every layer because you cannot do a parallel processing. Because if you do a bidirectional LSTM in every layer, then you have to wait for that layer, both LSTMs, to finish the work and then process it. Because of the complexity of the data they're doing it, they wanted actually parallel processing. So they used the bidirectional LSTM only on the layer 1. Residual connections. Another technique was invented around 6 months ago, 1 year ago, where at every layer, when you stack LSTMs, from the bottom LSTM will send its hidden state to the one above, and that becomes the input, and the next LSTM gets the output of the previous LSTM as input. But residual connections include not only the hidden state getting translated from one to the other, the input also gets inputted at every time step. So at this layer, I think you can see. At this layer, or even going up, you're not only getting the hidden state of the previous layer, but also getting the inputs. So again, the neural network model is getting more and more intelligent by this data. That's the residual connections. They've implemented attention also. They've used low precision floating point arithmetic because they figured out instead of using 64-bit or 32-bit or 16-bit, they went down to I think 8-bit floating point transactions because they found the accuracy is not affected too much, but computations improved really high. So really become short fast. They implemented beam search where they picked I think top 200 words, which is really complicated. but still I think they've used some 20 GPUs, I guess, to do the processing. They also have a dictionary, separate dictionary for just the rare words. Instead of putting all the words into the dictionaries of encoder and the decoder, they have a separate dictionary of just the rare words, and they have a one-to-one mapping for those. So whenever you find a rare word in the source, instead of doing an actual translation, you just go to that dictionary, pick up the word, and then put it into the translated sentence. So that way you don't have to have a computationally expensive model, but you can still address the UNC words, the unknown words. So this is the pictures of residual connections. So Google neural machine translation model is the state of the art right now, unless someone else comes out. I would want you guys to go look at the TensorFlow website, where they have given just two set of files. You have this data utils file and the translate. These are just the two files which will show you how to translate from one language to the other language. They actually provided the data set too. You can download the data set and then run the program. You can see just the data utils part, which is actually pre-processing of data. Maybe it's around 300 lines of code, and the translate model, I think maybe 100 lines of code. So just 400, 500 lines of code. You can actually have a neural machine translation model available, which gives a real high blue score for, I think, a couple of languages. Lot more research expected, where people are looking at, instead of having only one language to another language, can I have a model which translates from one language to n languages? So one to many, and they're also looking at how do I do many to many. So I have English and German, but I want to translate that into, let's say, French and Chinese. How do I do that? Can I train a model which can take both English words and German words, and it knows, when it reads a word, it knows whether this is a German word or not? And there are a few techniques available. Actually, you tag each word with a language code. So for a English, you have a @en in front of each word, and for German, DM, I think something they use for. So you actually can tag the words and put them into one single dictionary, and then use that for translation. So more research is happening. I'm personally quite excited about what's going to come. But if you really want to mess around with the translator, go to Google Translator, open up two Google Translators, and you say a sentence in English and select, say, to German, and then the other model pick German to English, and let both the models talk to each other. And then see eventually whether the original English sentence remains the same or not, or it just screws up. It's really funny, because after some time, the original English sentence is gone. It's actually talking something else, because the translation is not really that effective yet.
It happens with humans that way.
Oh yeah, of course, yeah. Anyway, that's all I wanted to talk about today. If you have any questions, I'll be happy to answer. Yes. You're right. In addition to what you said, gender is one, but more complicated things are, let's say, a word has multiple meanings, and the meaning is contextual too. Let's say the word bank. It can be a financial institution, it could be a river bank too. Models are becoming, of course, intelligent. They're not really perfectly intelligent to figure out. There's so many nuances, subtleties, which I think still models are not figured out yet. Yeah, gender is one of the first things, yes, which they have not figured out sometimes. But that's the fun of it. Like, if you want to really mess around with that, play two Google translators with each other and see what it is. Yeah. English. Yeah. Yes. Yeah. Yeah, that gives an opportunity for all of us, people like us, developers. We can actually develop better and efficient models who can do more better translation. Yeah. There's lot of work to be done. And if you're a programmer, if you really want to develop programs, all the frameworks available is making it so easy for you to program into this. You can, for a simple data set, you can write NMT in maybe 1 or 2 hours. And if you really want even a production ready thing, maybe I think a couple of weeks, I think you can write a production ready translator. But of course, you need to have real bigger data sets and stuff.
So one of the issues that I deal with regardless of the application, is replicating. So let's say you write this Google paper that you were talking about, right? Assuming I had the hardware for trying to replicate those efforts. Typically what tends to happen is there is a lot of hyperparameter training that goes underneath, especially with the more complicated architectures. And so I haven't read this paper obviously, so I don't know how Google did it, but in a lot of cases, no one really mentions in literature how they went about doing hyperparameter training unless the paper was specifically on using evolutionary algorithms and something like that. So in this particular field and these applications, what is a more popular way of creating the hyperparameters, like picking the architecture size, the number of bit layers, whether you want to use Adam or SGD or any of the popular algorithms and algorithms?
Actually, I'm about to write a blog on exactly that topic because I've been thinking about a similar thing, and some of this presentation, and also a month ago I did a presentation on summarization, and then I talked about some hyperparameters too. Some papers do talk about what parameters they have used, and also if you look into some of the Stanford courses where they're teaching, some of those professors who are really experts in these areas, they actually talk about the hyperparameters too. So some of the collection of best practice I want to actually come out with a blog in terms of, okay, what should be the size of the LSTM, what should be the dimension, what should be the size of the vocabulary, what should be the activation functions you got to pick. All of those hyperparameters I want to actually tabulate. But then, in my opinion, I think when people write the paper, there is a very negative thought process about the paper. All these technical papers people who write, they are not writing for the purpose of educating people. They are written with the purpose of showing how great they are. And hence, I think all of us in the world where we are trying to learn, there's no other way of learning other than reading technical papers, but they are not written with that. So it's always slower process. And the books and being written on blogs will help, but I think things are changing so fast. But I would say some people do want to, like the Salesforce recently hired a guy who I personally believe is like almost like a god in the NLP world. His name is Richard Socher. He's a Stanford PhD a few years ago, and he has his own company. And I think some of his papers, I think he actually talks about the hyperparameters they have actually selected. So some of the papers in the last 6 months I've seen, they do have a section called experimental settings, where they actually explain how they've done it, how they actually implemented the hardware and the parameters and all of the stuff they explain. But I see your point. Yes, I think it's that's where the whole issue is sometimes.
It's more from what you said, like now you have Keras and you have TensorFlow, so it's easy to set up the architectures.
Yeah.
But depending on your application, you don't know how to really pick this.
Yeah, that's part of the hidden trial.
And it's hard to give a good rule of thumb.
Yeah.
All these do this, all these do that.
That's right.
So, one important factor in all of this is measuring, like for instance the blue score, and you already pointed out some of the issues with the blue score, the order of the words. The words might be perfect, but if they're in the wrong order, then it's meaningless.
Yeah.
So the company that I'm with actually developed a different measurement tool that we call a trust score, and it's based on the if the information in the sentence is actionable or not.
Mhm.
So it's just a different measurement tool.
Got it. Yeah, that's nice. Yeah. Yeah, I'm sure. I think this field of study, I think, needs a little more mathematical, a little more non-subjective way of measuring the accuracy. And
Yeah, so that's kind of we use it in a commercial sense, in the real world. If someone can't understand, the output of the machine, the translation engine, then it doesn't do my client any good.
yeah, yeah. Beautiful.
I have the same question, but on the top of that, like, for instance, in the for optimal parameter, we develop a network and have a network. In the real world, like, if you have any machine learning system which is currently going on, and there's some issues like the false positives coming up, with the classical machine what's the ideal strategy to analyze these kind of information?
Yeah, I know it's a different question. The basic thumb rules, what I've seen based on whatever papers I've been reading, and if you look into all my slides, every slide there's some reference to the other. What I've found is keeping it simple always works. Number one, and it's also easy, even though you may lose a little bit of accuracy, but I think the development, training, and upkeep of the model I think is easier and faster if you actually keep it simple. So the number of layers or bidirectional, unidirectional, what's the dimensions of the input or the dimensions of the output, or the captures or whatever, all of these things, people are going for a simpler methods. For example, just let me take an entirely different example. Image processing. The last, I think, image processor, which is it's called ResNet, which came out with Microsoft, I think, a year ago. They have around 100 or more than 100 layers of CNNs and all the stuff, convolutional neural networks. They could do that. I think the model was trained for almost 3 weeks on multiple GPUs. That is beyond the reach of individuals or even smaller companies. I think the only big, massive company can afford to do that. But then, if something goes wrong, I think it's difficult to figure out what's happening. That's why all the papers right now, people are talking about, even if it's baby steps, at least we know what's happening, and then why don't you make a small incremental improvement in the model? And I'm actually waiting for a time where, see, when the neural network was introduced, then you actually have RNNs invented, then LSTMs are invented. I'm actually looking for a next model which actually will make it even more simpler, because you don't need so much of mathematical calculations, I'm guessing, to figure out the wisdom in the sentences. And I don't know, I'm sure there should be a time where people should get Nobel Prize just for that, because that's going to be a tremendous step forward in making things easier on just processing text. And I'm sure similar growth is happening in ML world too, but just in NLP world, I think.
So one approach that some people are taking are weighting the components. You know, you can tweak, if you weight certain components more than others, it ends up building better results.
So right now, I think you mentioned, I think it's more of a hit and trial right now. I think there's no absolute science available. There's a few tricks available for people are trying to share with each other, and you're trying to do that. But yeah, there's no one single easier way of doing it. Yeah.
Do you see a role for bringing etymology into this problem? Like, suppose I had the word interstellar and it was not in my vocabulary. I could try to break it up and say, well, inter means between, stellar is star, and kind of a reasoning. I mean, it's completely orthogonal to sort of this training-based thing, but it may enhance the accuracy of that.
Sure. So I think I mentioned briefly, if the word is not available in the translated in the target language, I think you actually start breaking it down. You break a word or a phrase into smaller pieces that can be even go to the level of the characters, and then go back and rebuild the word and then do the translation. But there's not enough of corpora available, I think, to train models intelligently. Right now, you have only corpora available for full words and full sentences, and that's where the models are right now. But I think maybe in the next 6 to 8 months, you may see more data sets available which actually can break down the words into smaller pieces. I think it's taking more time for people to create the data sets. Actually, if you want to set up a company, I would say don't start a machine learning company. Start a company which actually creates data sets. There's a huge amount of money available just to create data sets. And you can go to a third world country where we can do some tagging or whatever. I think you can do a manual labor. But once you create the data set, I think it's so valuable, because the same data set is being used by so different people and makes sense out of it.
I want to know, when you process images and process voice, right? Images are static, so you can go and look at image, interpret what is written in the image. When you look at voice, can you tell, what would be the things to look for if there is real-time voice, somebody speaking and you want to do a real-time translation, and how does that work? What is the complexity that you need to look for?
Yeah. So there are two parts in it. One is, of course, real-time part of it, where it's more of how quickly the model can turn around and respond. But if it's a temporal, let's say you have a sentence or it's a video. So it's a video as opposed to a still image. Still image does not have any history, it's just an image. So even LSTMs and RNNs actually will capture the temporal aspect of it. So if the current word is sad, you need to know what the previous two words are to understand the meaning of sad right now. And the temporal aspect, I think there are models available, whether it's in the image processing, it's called CNN, convolutional neural networks, and in text processing, it's RNNs and LSTMs, GRUs being used, which actually capture. But once you capture the temporal aspect of it, how quickly you can respond, like a real-time response, I think it's a combination of so many other factors, including the hardware and the software and the processing and all of that stuff. Yeah.
There's a lot of disciplines involved.
Oh yeah, there's so many. If right now I think Google actually has free APIs available. You can just go online, then do a copy paste an image, and then immediately tells you what is in the image, etc. And it's just almost like a split second. So they have figured out a beta version of it which actually can do it, but then but that's a generic images. If you're really into, I was talking to a person the other day who wants to start a company where she's talking about furniture. If you want to have a living room with let's say a couch and a carpet and walls and the wall paintings and stuff, and you have seen that in some magazine or someone's house or on a video, you get the picture, give it to the model will figure out first of all what is in this picture, and identify individual items, and then identify comparable individual items, and then bring all those. Let's say you have a chair, identify 100 chairs. If you have a carpet, identify 100 carpets. And then with these 100 carpets, 100 chairs, 100 couches, 100 walls, can you make intelligent living rooms and give a few combinations? You can have, worst case scenario, a yellow couch with a blue this and a black walls. Even though theoretically it's possible, no one would like it. So you actually have not just the mathematical possibility, but also you need to get the human sensitivities too. So that's what they're developing a model of just a given image, it will figure out what would be a comparable image for you. And yeah, that's another problem statement I think we'll work about.
You talked about the view score. How much is it from the speech to text and then text to identify like the multiple different things? Like you said, it's 40% correct. So how much is yours from the speech to text?
I don't have the numbers for the speech to the text or the speech to speech. I'm more focused on the text processing right now. There was, I think, earlier study was if you have a speech to speech, it used to go through the route of text, speech to text to speech. But now there are research going on, some published but some unpublished, from the speech directly going to a text. So source speech, but the target is already a text. They're trying to develop a model which actually can internalize the sound waves and translate into a text. But I don't have the numbers about how it is because I think it's still in the research phase.
And are you moving anywhere more towards the idea of the actions? I think that's what you were talking about, the score, other kind of score. It's like, I think personally it's a dumb way moving from one language to another based on the characters of the sentences. I think as we grow, we actually think about the idea rather than the language or the words itself. So are we thinking about that at all, like in terms of idea of action?
Good point, yeah. So some time ago, people have converted words into vectors. Now we are talking about sentences into a vector. So instead of each word, let's say if a sentence has 10 words, it will be 10 vectors that will signify the meaning of the sentence. But now they're talking about one single vector which actually captures the entire sentence and its message too. Once that is widely used, most probably people I think can get to that. Right now the model still, even though it's a word to word to word, which is actually it's still capturing some of the information, but I personally believe the accuracy, the blue scores are so low for the models just because there's not enough of corpora available. The hardware I think is okay, fine, I think it will run for the current situation, whatever we have, but not enough amount of data sets available to actually have to train a model in. You need to have not just millions, maybe even billions of data sets, billions of sentences to available to translate. That's why language models are available easily because it just had single monolanguage lingual corpora. But bilingual corpora I think is not available because you actually need to have human beings sit down and start writing what the sentence translation sentence is.
I think what I'm talking about is train a model not only with the text, with the image, with the idea of like walking. So like this guy is walking. Put an image also there.
Oh yeah.
The model will understand.
There is a paper published called show, tell, and write. A model which actually looks at the image and actually tells you what's happening in the image. Yeah, they are already ML. So then you're talking about two sections of ML combined research into image processing and text processing.
Because then it will eliminate the idea like altogether. So once the system has the intelligence in terms of idea of the walking, running, then it's independent of any language, and then you give it a vocabulary of any language, and it will create a sentence for you
Sure.
based on that idea.
Sure. Yeah. The research is happening there. Yeah, I'm not an expert on that, but yes, I've read a few papers on that. Yes.
There is public information about how to create hidden vector.
How to create what?
Hidden vector. Or what kind of attributes are used to create?
That is what an LSTM does. So you give an input, so you define a model LSTM, and then give an input, a series of inputs, and at the end of all the inputs, it automatically creates. That is the primary purpose of an LSTM or a neural network. It creates a hidden vector because that is in other words, the soul of the neural network. Because hidden vector actually encapsulates the entire sentence or entire input you're given. So you automatically get it. Yeah.
That's part of the training.
As part of the model itself, when you initiate a model and give an input, that is the only output. You get a hidden state out of it.
This training is based on some of the heuristics of how people like human heuristics.
No, they want to take out that aspect. So you have a input sentence, you have a output sentence as a source language, a target language. You give the input language, it thinks. Let's say the cat's out on the mat. Let's say that's an English sentence. In French, it gives out a wrong sentence, but you know the right sentence because you have human curated data set available. Then you tell the model that's not the right sentence. This is the right sentence. Go back and change your weights. So it goes back and change the weights in the hidden state, and then the hidden state. And if you do the same thing maybe millions of times, eventually the hidden state actually is becoming intelligent enough to capture for any sentence you input, it knows what the answer is.
This training of the machines, the automatic way to train, also is for humans that not.
No, that's the whole of machine learning where you actually have the frameworks available. You can write a few lines of program and then tell your just a regular CPU itself is finished. Let's say if you have a Mac or a Windows machine, it does it and then it's ready to do translation. Yeah. So this particular there's programs available given by TensorFlow by Google. If you download those files and then run it on your machine, it actually shows the translation part of it. It actually creates a model, and then any new sentence you give, it actually translates.
Yeah, I was just looking at it, but the training is already done.
You can get a trained model, but if you want to train yourself, you can do that too. Yeah. You have pre-trained models available because people want to do enhancement on the existing models, then they download the models. Because some of the models, pre-trained models, are trained on massive machines, which you cannot do it, but you can do incremental improvements on the pre-trained models, and hence you can download it. Otherwise, you can do it yourself. Actually, I have trained a model on summarization, and also I've trained a model on question answering, where many of you guys, if you don't know, there's an Indian book called Mahabharata, which actually is a huge volume of stories. So I've trained a model which will understand the whole story, and then whenever you ask a question, it actually gives an intelligent answer. Also, this was a data set which was not humanly curated because we downloaded the whole story and then broke that story into small pieces of sentences, and we trained the whole the model on the whole story, and then it became intelligent enough to answer questions. But right now, if you look at the whole question answering section of NLP, it gives only single word answers or maybe single phrase answers yet. It is not like a human being. If you have read a book and then now tell me about the election process of the United States, you may be able to give a few sentences. But the model has not become that intelligent to give a long answer. But yeah, you can do the training.
Can you mention some of the best use cases, marketable?
For summarization, I think news agencies are using it a lot. Let's say you have a massive news article that comes in. If you want to make a summary, small bullets, or even identifying the title of a news item. There's one story. Question answering is being used by even doctors in hospitals, or even lawyers, or even individual citizens. There is one company as I met the other day. They are trying to, of course, they are using a lot of lawyers also to make answers. They're developing a model where, let's say you are a citizen and say, I was driving fast today, about 5 miles above the speed limit. Cop gave me a ticket. What chance do I have if I go to the court and fight it? And if you ask that question, the model will figure out an answer and then gives an answer based on, let's say, stories. This guy, that guy said, this is a story. So it picks up the information. That's another. Similarly for patient also, if the doctor wants to find out what would be the right trial, human trials I can recommend for this patient. There are actually a lot of companies. I was talking to a company the other day in San Francisco, which actually identifies the right trial, human trials for a patient based on so many factors. So that's another use case too.
But Watson is already doing that, right?
Oh yeah. Yeah. So the similar models people are developing. Actually, if you look at healthcare, is one vertical which is getting a maximum amount of investment in the whole ML world. Because I think everyone is trying to find some improvements in the healthcare. Yeah. And in product companies, let's say if you are a sales guy, if you want to find out what my stock price is going to be, or what my sales are going to be, or even product information also, you can use this ML or NLP processing.
Just one more question. The financial report, is anybody using the actual analyst reports or the economic templates, using that to compare a bunch of companies' performance, stock performance, future forecasts?
Yeah.
Anybody using that?
Lots of companies. Actually, I know a company in San Francisco. When we make a stock price prediction, let's say all of us when we are investing, we would look at the company and say, Google is a good company, or Apple is a good company. Okay, maybe the stock price will go up in the next 6 months, so let me buy. So we make a judgment based on the past history of the company, right? There are machine learning models being developed which will predict the stock price of a company, not just tomorrow, maybe 1 week from now or 1 month from now, based on not the previous stock performance, based on rainfall, based on number of tweets of Trump, or terrorism activities. People are trying to figure out the causation of stock price movement based on factors which are completely irrelevant. For example, rainfall versus stock price, terrorism versus stock price, Trump tweets versus stock price. People are trying to find out. And this is in addition to the regular sensible information like, okay, analyst reports come out, or let's say a new product is released, or in China or Japan or some other country, the political statements are the following. Can we study these texts and make a very quick judgment about what will be impact of that on the stock price when the market opens? For example, if there are 10 different terrorist reports which has been published in some country, ABC, and if you think that's going to be it's going to have an impact on your stock price, if you have to be up in the night to read all the news item and talk to people, but if you have a model which actually can analyze the whole thing and make a prediction. Maybe I don't know the numbers, but I think in financial investment, I think is this next area where people are trying to use ML. Actually, there's a company called Startup.ml. I think you guys should check out the website. They take lots of interns and they take live projects from hedge funds, and they're developing models to help hedge funds predict the stock price variations based on so many natural and unnatural factors. There's no area I can imagine where ML cannot be used nowadays. I think it can be any damn thing.
I wonder if that could also be used to find dishonest dealings in the marketplace as well.
Yeah.
You see the application for product configuration, because you want to go from an English language type intent to CLI, or to program a device to do a specific function.
I guess I don't understand the question much.
So let's say I want to configure a router and I want to set up a VPN network. I can say that easily, but now I want to translate it to particular CLI based on the context and based on certain natural language input.
Yeah. There is enough research on preventive maintenance based on numbers. For example, you have IoT data coming in and then actually using the numbers, it can do some corrective actions. Now the research in using those IoT data plus text, trying to do some corrective act, can the machines learn themselves by looking at the text and also the numbers? That I have not seen published reports yet, but I've seen lots of, even in conferences too, using the IoT data and do preventive actions. If you go to Microsoft Azure website, they have so many case study use cases published by airline companies, and even GE actually has a lot of factories where they are maintaining based on the IoT data. So I'm guessing they're using the text also soon. Okay, thank you very much. I really appreciate it. Thank you. Thank you.